Hello, my name is Evan Johnson, and I'm presenting the work that me and my co-authors have done on building a safety verifier for compiled WebAssembly code. WebAssembly is a modern, platform-independent bytecode originally intended to be embedded in the browser. It was therefore designed with isolation in mind, and many of its design decisions are in service of making it easy to constrain the data and control flow of WebAssembly programs. For example, WebAssembly exposes 3 distinct memory regions which are each accessed with their own instructions. The stack contains the local variables for WebAssembly functions and is accessed via the get and set functions. Linear memory is where arrays, structures, and the program heap are stored and is accessed via the load and store instructions. Global variables also have their memory region. However, it is rather uninteresting and I will not discuss it much this talk. Control flow in WebAssembly is structured. There are only 2 types of indirect control flow transfers, both of which are structured in a way so that control flow integrity is built right into the language. All these design decisions contribute to making WebAssembly safe when embedded in the browser. They also make WebAssembly an attractive option for sandboxing code outside the browser. For example, the Cloudflare and Fastly CDNs run many tenants in the same address space on their edge cloud using WebAssembly. WebAssembly serves to isolate these tenants from one another, preventing them from reading each other's sensitive data. Similarly, Mozilla uses WebAssembly to sandbox third-party C libraries in the Firefox browser. This is done so that the bugs in these third-party libraries cannot be used to compromise the rest of the renderer. This isolation is enforced by the WebAssembly compiler. Specifically, WebAssembly compilers enforce a form of SFI. That is, they constrain the memory that WebAssembly code can access to a subset of the address space. The compilers do this by inserting dynamic checks when compiling WebAssembly to native code. For example, for the code running in Sandbox 1, the compiler inserts checks instrumenting all memory accesses to constrain them to that Sandbox 1 memory range. This means that even if Sandbox 1 is running malicious code, it can't interfere with Sandbox 2 or the runtime. This is great. It means we can run many sandboxes within the same address space without worrying about interference. When we do this though, we are trusting the WebAssembly compiler to put all the right checks in all the right places. Unfortunately, this trust is misplaced. A bug in a popular WebAssembly compiler allows programs to read outside their sandbox. The code that can be used to exploit this bug is a simple switch statement inside of a for loop. The loop iterates 10 times, and the switch statement switches on a constant case number each iteration. I'm going to walk you through the x86 code produced by the buggy compiler, but don't worry if you don't feel like reading x86 right now, it'll be quick. First, we check the case number, which is stored in RIX, to make sure it's valid. Then, we load the address of the appropriate case into RBX from the switch table. Finally, we jump to the appropriate case block. This code is safe because we check that this switch table index REX before we use it in the memory load. The code I showed you is before optimizations. The optimizing compiler tried to get a bit more clever and lift the load above the loop start to avoid performing this same load 10 times. But the compiler forgot to move the check. Unfortunately, this means that we have an arbitrary read gadget, and as an attacker we can read outside the sandbox region. And when isolation is broken, bad things can happen. Clients on a serverless platform can read each other's sensitive data, or buggy third-party libraries in a browser can compromise the renderer. So, if getting isolation right is so important, and we can't trust the compiler to always get it right, what do? We could build a verified WASM compiler that never produces an unsafe executable, but this is painful, and we already have solid industrial compilers like Lucet and CraneLift. Like previous work on SFI, we instead propose to verify that the binaries produced by these compilers are safe. In the rest of this talk, I will present VeriWasm, a verifier for native compiled WebAssembly code. First, we'll talk about how VeriWasm checks WebAssembly's SFI guarantees at the binary level. Then, I'll tell you about our effort verifying the verifier, and briefly describe our evaluation, using VeriWasm on production binaries and catching unsafe binaries due to compiler bugs. To verify the safety of the compiled WebAssembly, VeriWasm checks that all necessary safety checks have been preserved during compilation. It takes as input a WebAssembly binary. For our purposes, we produce these binaries using the Lucet WASM compiler, the compiler used by Fastly and Firefox. VeriWasm checks binaries in 2 phases. First, it disassembles the WebAssembly code. Then, it uses static analysis to prove that all loads, stores, and control flow transfers are safe. The idea of disassembling and checking sandbox code post-compilation is not new. Many SFI tools, including native client, had verifiers, but checking code produced by WebAssembly compilers, in particular Lucet, has a new set of challenges. At the WebAssembly level, the three memory regions are accessed by distinct instructions, but at the binary level, the distinctions between these regions gets muddled. All we have is a move, and we need to check whether it is safe or not. Determining precisely what address a move is reading from or writing to, and whether that address lies within the sandbox's memory range is difficult in the general case. This is further complicated because WebAssembly compilers add safety checks before performing optimizations, and checks can be moved or, when redundant, removed. And we really want compilers to do this. Consider the following code which reads from the same location. Without such an optimization, we would perform two bounds checks when in fact it's safe to remove the second check. We want the compiler to remove this check, but we also need to account for it doing so. I'm going to show you how we overcame these challenges in VeriWasm in the next few slides. To start, I'll note that we don't need to handle arbitrary assembly code. All we care about is the output of existing WebAssembly compilers, and these compilers preserve WebAssembly's structure at the binary level. As we mentioned earlier, there are only two stack operations in WebAssembly, get and set. All they do is read and write to local variables. This is great because it means the output assembly will also be very simple. Much like in WebAssembly, compiled code should only access the stack at constant offsets off the stack pointer. This makes stack operations much easier to check since we only need to be concerned about this restricted semantics. Similarly, there are two operations on linear memory, load and store. They aren't quite as simple as stack operations because their arguments are variable offsets, but they also only produce restricted x86. For example, at the assembly level, there is a third argument that represents the start of linear memory, which is implicit in the WebAssembly code. In the Lucet compiler, this is held in the RDI register. So, at the assembly level, if we know that one of the arguments is the start of linear memory, then we know that it is a linear memory load or store. The structure of control flow in WebAssembly is also preserved at the binary level. There are only two types of indirect control flow transfers, one that resembles a C-switch table and an indirect call. There are no go-tos. And both these control flow transfers use static lookup tables to get their targets, which makes them easier to reason about. VeriWasm takes advantage of all this structure to verify native code. VeriWasm uses 4 specialized analyses, one for each memory region and one for control flow. Since these analyses are specialized, they can take advantage of the preserved WebAssembly structure. Let's take a look at how VeriWasm checks linear memory isolation. Here is a function foo that simply performs a read from linear memory and then calls a function bar. Our linear memory checker ensures that all loads and stores actually land within linear memory or the guard page after it. To check the safety of this function, we need to check that this load from linear memory, RDI plus RIX plus hex 48, is within the region 8 GB after the linear memory base. The checker does this by analyzing the function line by line and collecting facts about the registers and stack values as it goes down. At the start of the function, all we know is that RDI points to the start of linear memory. We assume this for all functions. We know nothing about any of the other registers or contents on the stack. The first instruction truncates RIX to 32 bits, so now our checker knows that RIX is less than 4 GB. The second instruction is a read from memory, so we want to check that this is actually within the linear memory. First, we check that RDI still points to the start of linear memory. Then, we check that RIX is less than 4 GB, which it is, since it was just truncated. Finally, we check that the constant offset is less than 4 GB. Since we know that RDI points to linear memory base and the two arguments are less than 4 GB, then the memory access must be within the linear memory region. We can conclude that this load is safe. The last instruction is a call to bar. We don't enter bar, we only check that RDI still points to linear memory. This ensures that our assumption of RDI being the linear memory base holds. While I don't have time to go into similar detail for the other analyses, I can maybe tell you about the insights that make them work. Our second insight is that we don't need to check WebAssembly's full semantics to ensure SFI safety. For example, for control flow safety, we don't need to check WebAssembly's fine-grained, type-based control flow integrity. All we really need to check is that every call targets the start of a function since we check each function's safety. For stack safety, we similarly don't need to ensure that the native code follows WebAssembly's restrictive stack semantics. Let me give you some intuition why. In WebAssembly, if you have a function foo that calls a function bar, WebAssembly semantics specify that bar should not be able to read anywhere on the stack outside of its own stack frame. Verifying this would be needlessly hard. For SFI safety, it's sufficient to prove that bar can only write to its own stack frame and thus can't clobber return addresses on the stack. But we don't need to restrict bar's reads to its own stack frame, it's safe for bar to read the whole WebAssembly stack. This ultimately means that we could get away with a simpler and less precise analysis. Alas, we still need to reason about optimizations. One optimization pass we ran into in practice is instruction reordering. Here, the function foo performs an indirect call to the function specified by x in the function table. It does this by creating a variable, func_offset, that indexes into the function table from x. But the offset into the lookup table is created before x is checked. The function offset created from x is safe only if x is later checked to be within the table. To solve this problem, we use a new analysis technique called dependent abstract variables, which track relationships between variables and ensure that when one is used, all the variables that it depends on have also been checked. In this example, it tracks the relationship between x and func_offset. You can read our paper for more details. We went over the 3 local analyses that VeriWasm performs to ensure SFI safety. How do we know that these local analyses actually give us the guarantee we want, that malicious code is actually isolated? To prove that our analysis guarantees isolation, we did the right thing and formally verified the static analysis algorithm in Cuck. Specifically, what we prove is that if a WebAssembly program passes all of VeriWasm's checkers, then the binary is isolated. To verify VeriWasm's analysis, we created W64, a small DSL which models the subset of x86 which the Wasm compiler can produce. With W64, we don't have to model all x86 to prove that our verifier only certifies safe programs. Instead, we recreated our static analysis to operate on W64 and prove its correctness. While this wasn't a verification of VeriWasm's Rust implementation, it does verify that the algorithm we use correctly certifies safe programs. It also helped us find some bugs in VeriWasm's analysis. Some of these bugs were simple things that we missed, like checking to ensure RDI was set to linear membase at every call. Others were more subtle. For instance, as I mentioned earlier, VeriWasm says it's safe for a function to read the whole stack. This means that we need to make sure a function can't underflow the stack and, for example, read what may be another sandbox's memory region. We didn't account for this at first. And to address this, we had to modify our analysis to limit reads in the caller stack frame to 8 kilobytes, the maximum number of arguments that the WebAssembly compiler allows. Okay, now we know that VeriWasm actually ensures isolation, but how does it do on real code? To answer this question, we used our Rust implementation to verify WebAssembly binaries from 5 sources. We checked 2 production codebases and 3 additional sets of benchmarks. The production code we verified were the 3 libraries from Firefox that are deployed as native WebAssembly code, and 101 production binaries on Fastly's serverless platform. Verifying these applications took on average only a few seconds, which is fast enough for the use case of verifying binaries as part of a continuous integration pipeline. We also verified the 13 spec benchmarks that can be compiled to WebAssembly, and the Lucid compiler's benchmark suite. Finally, we verified 20 million randomly generated WebAssembly programs to more thoroughly test our tool. We didn't find any new bugs in Lucid so far, which is good for Lucid but bad for VeriWasm. To check that VeriWasm can actually find bugs when they are present, we used it to rediscover 11 bugs that were found to subvert other SFI schemes. These bugs represent tricky edge cases discovered by other researchers in the native client, Pittsfield, and Misfit SFI schemes, as well as the bug mentioned earlier in Wasm SFI. When bug reports included proof of concept code for the bugs, we check that code directly. Otherwise, when the bug report only included a description of the bug, we hand-wrote assembly code with the vulnerability. VeriWasm successfully flagged all these bugs. In summary, VeriWasm verifies the safety of native compiled WebAssembly code. It exploits the structure of WebAssembly code to make this possible, even in the presence of compiler optimizations. We verified that our analysis really ensures that the code is safe, and we tested it on compiled WebAssembly being used in production by Fastly and Mozilla. You can find the source code of VeriWasm at the link below.